In today's class, I will talk about spatial networks. So spatial networks are simply networks which are embedded into some space. And in particular, we can say that the network is spatial as soon as we can say that the probability of observing an edge between two nodes depends on the distance between those nodes. So we will see in more details what it means a distance, what it means the position of nodes, and what space can be. Of course, a typical example is, as you can see on the picture, when points are embedded into geographical space, so identified with a latitude and a longitude typically, and but this is not the only possibility. And the same thing when we talk about distance, we will see that we can talk about physical distance, but also things like economical distance, social distance, or other kind of distances. I want also to stress that many elements of this class are taken from this review from Marc Barthélémy. So if you want to know more on the topic, I encourage you, well, it's a good place to start. So what are the different types of spatial networks? Here are a few examples. So typically you have networks embedded in the geographical space, like here some transportation network dataset, but it can be any social network also. For instance, nodes are usually embedded into space, even if you represent individual people or if you represent interactions between cities. So these points are embedded into a space. So typical examples are like this transportation network, like airlines, bus, subway, ships, and so on and so forth. Embedded in the same kind of geographical space, you will have infrastructure networks with roads, power grids, and the internet. But you have other kinds of networks, for instance, a neural network also, in which, for instance, if you think about a neuron or about areas of the brain, they have some position inside the brain. And so you can study it in terms of this relation between edges and distances in the brain, for instance. Same thing with proteins, in which you have atoms that are located in space, and the probability to have interactions between them depends on the distance in space. And of course, social networks and many other cases. So, as I said, there are many different spaces in which a network can be embedded. We have already seen examples of one-dimensional space, and with the random, the Weierstrass random graph, in which, if you remember, nodes are located on a circle. So it's a circular one-dimensional space. And nodes are connected to the closest nodes in this circle. So it means that the probability of observing edges between nodes depend on their distance on this circle. And when we start to add some random edges, we are breaking this impact of distance, but we can still define it as a probability that will decrease with distance. Another example we have already talked about is in Facebook. We have observed that the probability of being connected with someone actually depends on age. So individuals on Facebook tend to be connected with a higher probability with people of the same age. And so what this means is that if you consider age as a position on a space, which is a one-dimensional space going from, let's say, 13 when people are legally authorized to create an account on Facebook to, I don't know, 120. So this is the size of your space. And you have a position which depends on your age, and you can compute a distance to all the other individuals, which is the age difference. And since we observe that there is a higher probability of having edges between people who are close from you in terms of age, then it means that we can define this as a spatial network. Also, you can consider many other attributes like this one, for instance, political opinions. So if you use a spectrum from left to right, for instance, from -1 to +1, we have also seen that there is a higher probability of connecting with people who have a similar position on the political spectrum than you. There are examples. So the two-dimensional space, I have already addressed it, and three-dimensional space are typical. So I also gave already the examples of the brain or proteins. And but there are also possibilities of embedding in a space of higher dimensions. So one example would be when you have several different dimensions. So for instance, if you consider age and political spectrum and geographical position, so you have a large number of dimensions, and you can imagine that you will create a notion of distance between individuals that depends simultaneously on geography and political opinions and age and so on and so forth. But you need to define this a proper definition of distance, which can be difficult in this case. And we will see in a later class that graph embeddings are methods to embed graphs in high dimensional space. Well, they call it low dimensional space, but it can be, for instance, 100 dimensions. And thus you can study also the network well, it is embedded in a space, and you can study it as a spatial network in that case. But we will see this in a later class. So, as I already introduced this concept, the notion of distance is really essential in the idea of studying spatial network, because it's really what you will care about. So, each node has a position, which in this d-dimensional space, but between each pair of nodes there is a single value of distance. Even if you have one attribute, two attributes, more 100 attributes, from these attributes, from these coordinates in the space, you can define a notion of distance. And so between each pair of nodes, there is a distance between them. Several notions of distance exist. So the most simple one is usually the Euclidean distance. So if you have a space, I don't know, if you take a simple city, then you can just compute the Euclidean distance between points in this city, and this will work pretty well. Or if you have some abstract space, you can use Euclidean distance. If you have points which are located on everywhere, a little bit everywhere on Earth, so far away, you cannot really use Euclidean distance because the Earth is a sphere. So you need to use a grid circle distance, which will compute the distance between 2 points on a sphere according to the trajectory you need to take to go from one to the other, respecting the curvature of the Earth. In some cases, when it makes sense to multiply the vectors corresponding to the distance of nodes, you can use dot product or the cosine distance. So we will see this later when speaking about graph embedding. There is also the Manhattan distance, and I won't go into details. And the one which is, I think, pretty interesting is actually an observed distance, in which you won't really use some computation based on the two locations, two set of coordinates, but you can actually look in the data what is the time to go from one point to another. So, for instance, the time distance, if you're, I don't know, dealing with car trips, for instance, probably you need to take into account if you want to compute the distance. So instead of taking into account the type of roads you're going through and maybe the weather, average weather, and all these things which are quite complicated, you can instead measure what is the average time taken by people to go from one point to another, and this you can take this as a notion of distance. So the problem with that is that you won't respect really a metric space, but you can nevertheless work with this kind of distance if you have the data. So let's introduce the basic notation. So we will define this metric distance. So the distance, let's say the straight line distance, or the distance according to the metrics you have chosen between two nodes is will be represented by this delta. We can also define the root distance between two nodes with this L, which is so the root distance is actually, well, the distance you need to go. You need to go from one point to another if you follow roads. So if you follow in your graph the edges. So this is the distance. The root distance from U to V is the sum of all the distances between the dots, between the points, between the nodes on the shortest path. Okay, you take the shortest path, you take the sum of distances, and you get the root distance. And finally, the distance strength, which is the equivalent of the strength in a normal graph. So the weighted degree is the cumulative distance from a node to its neighbors. Okay, so or you can also study the average distance to the neighbors, which can be interesting to look at to study something like, for instance, if nodes with a high degree are connected to, in average, to nodes which are at a longer distance. So, or is it homogeneous and independent of node degree? So, is there a relation to the distance which is independent of your degree, or is it dependent on your degree? So from these three basic notions, we can introduce measurements as measurements of the network, which are the root factor, node accessibility, and global accessibility. So starting with the root factor, this is a measure of how directly you can reach a node from another one. So the root factor, or also they called the detour index, is defined for a pair of nodes. So it's how directly you can reach B from A. And so it's defined quite simply as the distance according to the Euclidean distance in this case, or to the notion of distance that you have chosen. And so you take this most direct distance between the two nodes, and you divide it by the actual distance that you will have to go through if you are following the path of the shortest path, the distance on the shortest path between the two nodes. So basically, if you want to go from A to B, following the graph, in this case, you will have to go first through this edge of distance 1, then through this one, distance 2, and then to this one, distance 1. So the distance here, L, the L distance is 1 plus 2 plus 1, it's actually 4. But the most direct, the shortest distance between the two will be a direct edge between the two that will have a distance of square root of 10. So your root factor is square root of 10 divided by 4. And this is also called the detour index because it tells you how much you have to take a detour to reach your destination. So if you have a small value, if your value is 1, it means that you can reach it directly. And then the higher your value, the most you have to take detour. The node accessibility is defined from the root factor and is simply defined for a node. So for instance, you want to know the node accessibility of node A, and you compute it by computing what is the root factor distance to all the other nodes. So how much you need to take detour to reach all the other nodes. So very simply, if you can reach all the other nodes directly, your value will be as small as possible. So in this case, it will even be 1 in average. So it will be 1. And the more you have to take detour to reach all the other nodes, and the higher your value will be. So it's the average quantity of detour that you will have to take, basically. And finally, the third one is the accessibility, which is also computed based on the root factor. It's the same idea as before, but this time among all the nodes in the graph. So you're taking all the nodes in the graph, and you compute for all the other nodes what is the detour index. And so this average value will tell you generally in your graph, if you want to go from one node to the other, do you need to take a lot of detour, or can you reach it by the shortest path according to your notion of distance? So the more your graph is connected through shortest paths that use the shortest distances, and the best will be your accessibility, so the lower score you will have. So we have finished this general introduction of what are spatial networks and basic measurement. And now I want to move to the topic of random models of spatial networks. So the idea is the same as before with the other random graphs. Either you want to test some properties, so you will just generate random networks and observe how much the properties of this the random spatial network will depend on some parameter or the other. Or you have an observed graph and you want to generate a random network that has the same notion of distance. You will impose the same notion of distance as your observed graph, and you will compare the two to see if what you observed on your original graph depends on this specific graph, or if it's just a consequence of it being embedded in space. So the simplest random graph that I have chosen is a random geometric graph, in which you take so you start by choosing a space, you distribute nodes randomly on this space, right? So if in the picture here, forget about the edges, we just put nodes randomly everywhere. Then we choose a radius, and we consider that we have a sphere around each of your nodes. So it depends on the dimension that you're using, if it's a circle, a sphere, whatever. But in this case, it's two-dimensional, so we will trace a circle around the node. And two nodes are connected if their spheres overlap. So if they are separated by a distance smaller than 2r. So basically, if the distance between two nodes is smaller than a given threshold, then you consider that they are connected. You add an edge between them. So the properties of this graph has been studied. You can check the reference, and it has been observed that the distribution of degree is actually Poissonian, like in a normal random graph without space. But the important difference is about the clustering coefficient. If you remember, the clustering coefficient was vanishingly small in Erdős-Rényi random graphs, in normal random graphs. But in this case, it can be shown that it has it's defined by this equation. And this D here is the dimensions. How many dimensions do you have? 2 dimensions, 3 dimensions, and so on. And you can observe that it does not depend on the size of the network. While in the problem with normal random graphs is that the higher the number of nodes and the smaller the clustering coefficient. And in this type of spatial network, the clustering coefficient does not depend on the number of nodes. So you can have a high clustering coefficient in a very large graph, which is a property of real networks. So a variant, I would say a generalization of this model is the soft RGG, which is more commonly known as the Waxman random graph. And so the idea is the same in the beginning. You start with putting nodes at random on a given space. But then you choose a notion of impact influence of distance, which is called a deterrence function. So we will detail what is a deterrence function in the next slide. But basically, you say that node has a distance, that the distance has a probability of observing edges, and you will generate edges according to this deterrence function, so according to the impact of distance. And if you choose a deterrence function, so f, if you choose an f which does not depend on the distance, so if your deterrence function is just equal to a constant, which is the typically the density of the graph, so the probability of observing an edge between two nodes, then what you get is the Ad-hoc random graph. Okay, so if I choose this kind of deterrence function in which the probability of observing an edge actually do not depend on the distance, then I get an Ad-hoc random graph. If I choose a deterrence function f, which is defined such as, well, the value is 1 if I'm below a threshold, and it's 0 if I'm above a threshold, then you see that this model will actually be equivalent to the one I just introduced before, the RGG random graph. So the deterrence function, which is actually really what defines the impact of space on this probability of observing edges, and it can be typically of there are two cases. The first one is when it's defined a priori, which means that we consider that we know already that, for instance, the probability of observing an edge will decrease according to the square of the distance, typically. So you can use, for instance, negative exponential, or you can use negative power, so in which the influence of distance will be so the exponential or negative exponential of parameter of the distance, or if it's a negative power, you will consider that this value will be, well, your distance at the power parameter, with alpha parameter. So this is the first situation. And the second situation is the one in which you want to learn from the data an ad hoc deterrence function. So you don't want to consider that you know a priori how the distance will affect, but since you already have observed data, you can fit what is the influence of distance on your data. But I will explain how later. So now let's move to a little bit more complicated random spatial graph model, which is the gravity law model, so the gravity model. So it's a model which is used since a long time, not with graphs, but with by geographers that are used to work with what they call origin-destination matrix. So you have an example of an origin-destination matrix here. The idea is that you create areas in your zone of study. So, for instance, let's say that you want to study, I don't know, the Lyon city. You will choose areas corresponding to neighborhoods, for instance, and for each neighborhood, you will count, for instance, the number of trips or the numbers of phone calls from one area to the other. So this A, B, C, D, E correspond to areas, and these values correspond to the number of bicycle trips, phone calls, or whatever between these two areas. So this clearly corresponds to a network, but often it will be much more dense because you typically can have, I don't know, trips between all the neighborhoods in Lyon. So the idea is that you have this origin destination matrix, and you count the number of individuals going from location I to location J, and this gives you these numbers. You have to be careful because the result, this matrix, will strongly depend on the zone that you have chosen, which is not the case, for instance, when you have a network with clearly defined nodes, such as airports in the dataset I'm giving you for exercises. But very often also we have the same problem because we use, when we study network, often the node can represent a country or an area like a neighborhood or whatever. So we often have the same problem, and we need to be careful about this notion of distance, because obviously if you take areas which are large, then you will lose some information of what's happening at short distances, for instance. So then the gravity law, the gravity model, tells you that the number of trips from location I to location J is scaling as this. So the number of trips is scaling as a notion of attraction of the area, so typically the population. That's why we use the P here. So the population of the first one multiplied by the population of the second one divided by a notion of distance, which is to the power of a coefficient sigma, which is either chosen, typically with a value of 2, if we want to really scale with the original law of gravity, but it can also be fitted to be another value other than 2. And so you consider the population. What is really important to remember here is that the population is used as a factor to explain the number of trips, and this probably reminds you of the configuration model, because in the configuration model, if you remember, we are using here the degrees of nodes, and the probability of observing an edge between two nodes depends on their degrees. And here it depends on their population, which is a kind of a proxy to the number of edges that you will observe, because it corresponds to the number of phone calls, the number of trips you will have. It depends on the number of people who are actually living in the city. So it depends on this population. So this is how it is defined in the geography scientific field. And here is a typical example in which you have an intercity phone communication. So the researchers have access to aggregated data about how many phone calls are made from one city to another. And if you observe what the network looks like between cities, you see that you have, well, big cities are kind of hubs, and some cities which are far away might be connected if they are big cities. So you see that there are quite a lot of calls from Brussels to Liège. There are connections between smaller cities which are close from each other, but you typically do not have connection between, I don't know, for instance, this city and this city and this one. So there is no strong link here. So there are not many calls between these two cities, even though they are at a shorter distance than these two, and these two have stronger links. Because obviously, even though they are at a shorter distance, they are smaller cities. So basically what this tells you is that the number of interactions between two nodes between two cities in this case depends on their distance and their total population. So similarly, these two cities, which are relatively big, do not have a strong link between them because they are far away. Okay, so the distance has clearly an influence. This is a fit in which you can see that if you estimate by a gravity model the number of phone calls in this case that you expect, and you observe the actual intensity of phone calls, you see that there is a quite good match. So this model of a gravity law of interactions seems to be a pretty good approximation. And here are other examples using different data. So railways and highways, ships, and so on. And you see that the authors, they fitted different gravity laws with, you see that they observed different, they use, so here they change the value of the sigma. Here it's 2, but here it's only 1, and here it's 0.6 approximately. And sometimes they use more complicated functions in which they try to fit, in order to fit more accurately, they need to add these parameters. So, okay, if we have to add 2, 3 parameters, then maybe it's simpler to just be more generic and to define this gravity law as simply a function of the distance times the product of the populations of the city. Okay, so basically, if you want to express how strong are the interactions between two cities, 2 points, how strong are the interactions, you can define it as the product of the population or strength of attraction, basically, and a function of the distance. And the question is then, what is this function of the distance? So as we have seen just before, you can use some predefined function with some parameters and try to fit those parameters. But different perspective is actually to learn it from the data in an agnostic way. So to do this, the simplest way to do is to cut space in bins. So for instance, let's say that here I have a bin which concerns all pairs of nodes which are at a distance between 0 and 100. So 100 meters, kilometers. Of course, it depends on what you're studying. But so you're taking all pairs of nodes at a distance between 0 and 100, all pairs of nodes between 100 and 200, and so on and so forth. And for each of these bins, you will compute the number of edges that you have observed, and you will divide by the number of edges that you're expecting. And this gives you a ratio, and this ratio will define your deterrence function. So for instance, here, typically, you observe that it's increasing in the beginning, and then it's decreasing. So this could not easily be modeled by some predefined function. It's better to just learn it from the data. So of course you have the problem of which bin you're choosing, but this is a different question. Typically, so if you choose an appropriate notion of distance, you can compute it this way. A little bit more formally, it is computed by, so counting, this is really counting the number of observed edges. And this corresponds to computing the sum for all the pairs of nodes. So all the pairs of nodes which are at distance corresponding to the current bin, we compute what is the probability of observing an edge according to a predefined model. So the simplest model consists in saying that all the edges are equals. So you consider that you have basically an Adoshreni random graph, and so that the probability of observing any an edge between any pair of nodes is just equals to the global density. But we will see also that you can use a different model and thus compare the number of edges that you observe to the number of edges that you're expecting according to a different model. So, so as you can see, this what's really interesting here is that we are computing for your network, for your observed network, what is the influence of distance, and then we will like to generate a random graph which is respecting this this exact influence of the distance. So now we have defined the general mechanism of the model, that the probability of observing an edge depends on the populations or degree of nodes, and it also depends on this deterrence function. So let's see how we can use this to define the network null model. And that's actually what we are really interested in this class. So let's consider that you have a spatial network that you have observed, so front call, strips, whatever. And you want to fit a gravity model which explains the best network. So if the population is not known, so if you don't have some notion of population, for instance, in the case of the airport dataset, maybe the population is not really meaningful. Or if you're observing maybe the, I don't know, a special network of the brain or proteins or these kind of things, there is no population that you can use that will represent meaningfully the nodes. So what you can use is the degrees of nodes. So you have to be careful with that, we will see later, but basically the degree of nodes tells you that you have, well, it tells you it's a proxy of the population, or it's just a proxy rather of the power of attraction of a node. Okay, so if it has a lot of edges, it's probably because it tends to connect to many other nodes, or it's attractive for the other nodes that create edges with it. So with considering that we have the population or the degree, we can fit our gravity model. So we learn the deterrence function, and we have a random model with a given edge probability for each pair of nodes. And this means that we now have this random model that we can use, and we can generate new graphs so keeping the same position for the nodes. So we keep the position of nodes, and we generate randomly edges between them with a given probability. And this probability depends on their distance and of their population. So this random graph model can be used to, just as any other model, as I said in the introduction, to compare your graph to this random graph. So if you compare the clustering coefficient, for instance, between your graph and the random one generated by the gravity model, the corresponding gravity model, what is the difference? But it can also be used for an interesting application, which is proposed here, which is the detection of space-independent communities. So if you remember the modularity that we have seen before, which is a notion of, which is used for the detection of communities. If you remember, when we want to detect communities by, we use the modularity maximization. So we want to find the group of nodes with the higher modularity score. And this modularity is defined as the actual number of edges inside communities minus the expected number of edges inside community according to a random graph model, a null model. And typically, with the with the usual definition of modularity, this random graph model is the configuration model. So we are taking the degrees of nodes into account, and the probability of observing edges inside community depends of the degree of nodes inside these communities. And what the authors here proposed is that instead of using the configuration model as a null model, they propose to use a gravity model instead. So they take their original graph, they fit a gravity model on this graph. They use this gravity model as a null model for a modified version of the modularity. And what does this mean? It means that you are actually removing the effect of distance. So this is the result they got. They computed first communities. So this is a network of communication and cell phone communication in Belgium. So they have, again, the number of phone calls between any two cities in Belgium. And on this network, first they applied the normal Louvain algorithm, and they got these communities with colors, right? And you can observe that these communities, they correspond to geographic areas. They correspond to regions, actually. They are very quite close to region in Belgium. And when they applied the modified version of the modularity, so a modified Louvain algorithm, which is using the gravity model as a null model, then what they observed is that they get something quite different, and they interpreted this as being communities corresponding to the language difference in Belgium. Okay, so you have two main languages in Belgium, and the red one corresponds to one language and the blue one to another one. So this can be interpreted as removing the effect of space and detecting something which was hidden before by this notion of space. Okay, so here you detect something which is interesting, it's meaningful. You're detecting areas that correspond to regions in Belgium. But since it's a spatial network, you're detecting something that actually you more or less already know, because you're detecting the fact that these nodes are close one from the other in space. But here, what you're detecting is something that was not known before, that was hidden behind this effect of space, which is that your country is maybe organized in two main parts. Okay, and this is maybe you're detecting communities which are more based on some social property, which was hidden by the spatial effect. So this slide is just to clarify a point about the deterrence function. So I introduced previously how to compute the deterrence function in general. And I said that you had to divide the observed number of edges for each bin by the expected number of edges. But for the gravity model, the expected number of edges is actually, you have to take the expected number of edges according to the taking into account the degree of nodes. So basically, the model you're using here as a reference is a configuration model. So more formally, you use this formula in which here you observe basically the configuration model. So you will divide the observed number of edges by the expected fraction of edges at this distance. But this fraction of edges expected at this distance depends on the degrees of node that you find at this distance. Okay, so this is just a detail about how to compute the deterrence function in the case of a gravity model. So let's finish with a simple example on Lyon. This is a work I've done a few years ago while working on a project on the Velov in Lyon. So you have these, so each dot here corresponds to a bicycle station of the Velov public bicycle system. And we have edges corresponding to the number of trips over a period. And we computed the deterrence function and we get something like this. And what is interesting here, I think, and important to show is that actually it's not monotonous. It has this property of decreasing in the beginning, then increasing, and then decreasing maybe more as expected according to the distance. And so here the distance is in meters, and what it tells you is that the distance which is more favorable for people to use a bicycle, a Velov bicycle, is about 1 kilometer. If it's less than 1 kilometer, people are not really as interested in using the Velov because probably because it has a cost in terms of finding the station and then taking the bicycle and again putting back the bicycle on a station. So maybe it's just shorter to walk if it's less than 500 meters or a few more. And also you see that the probability decreases with distance because obviously you don't take a Velov to do 10 kilometers. There are better solutions for that. So this is probably the good way to represent the influence of distance on your probability of using a bicycle, a Velov bicycle. So same example as the expert et al. Solution, in which here we detect first communities without considering with the normal modularity. So the typical, so using the configuration model as a null model. So without removing the effect of space. And you observe that the communities we find correspond quite well to the districts, the neighborhoods in Lyon, with the Croix-Rousse here and Villeurbanne around here. And here it's the 6, and I think this is about 3, or approximately the 7 arrondissement. So, okay, we see that we are quite well able to detect this organization of the space in Lyon. But what is interesting is that if you're now using the solution in which we are removing the effect of space by using this gravity model as a null model for optimizing the modularity, then we see that we detect some communities which are quite interesting. So these 2 communities that I highlighted here, which typically correspond to people following the banks of the rivers. Okay, so that's so maybe here students using going through the park and then following the banks, and same phenomenon here along the banks. Why? Because these are both convenient roads. There are bicycle lanes. It's beautiful, and also so it's convenient and it's used by tourists. So these stations, although some of them are quite far away from each other, they are in the same community, because if you remove the influence of distance, you have actually much more trips than expected between, I don't know, these stations and these ones, because they belong to this kind of community of banks of the Rhône in this case. Okay, so again, you're discovering maybe some social phenomenon using the banks of the river as a lane, at a bicycle lane, which was before hidden by the influence of space in that case. So you see that you don't really have these communities. So this is finished with the gravity model, and I will conclude by presenting an alternative, which is a radiation law, which is based on a quite interesting idea, a quite interesting observation of the weakness of the gravity law. So imagine that you have two cities which are at a given distance delta. Okay, so this is the distance delta. You have two cities at distance delta, and here you have two cities at distance delta. And let's imagine that these two cities, they have approximately the same population. Okay, the four cities here. Let's consider that we have taken cities of similar population. So according to your gravity model, the expected what the model predicts is that you will have the same strength of interactions. So, for instance, if you're studying phone calls, you expect to have the same number. You predict that you will have the same number of phone calls between these two cities and these two cities. But this actually seems unlikely, because if you live in one of these two cities, if you observe around, there are no other big cities around. So they are kind of the only alternatives. If you live in this city and, for instance, you're searching for a job, then and you don't want to go too far away because you want to go back to see your family, for instance, then you don't have much choice. Basically, you have to go to this city, and on the contrary, if you're from this city, you have to move to this one. So, of course, this is just a particular example, but you get the idea. The idea is that you don't have much opportunities. If you want to have more opportunities, you have to go much more far away. Okay, if you want, you need to move to, I don't know, this one or this city. On the contrary, between these two cities, clearly there are a lot more opportunities. You're going through a lot, you're in the middle between these two cities, you have a lot of different opportunities. You have capital cities, you have bigger cities, and so on and so forth. So clearly, you do not expect to have, even though we have the same population and are located at the same distance, you don't expect to have the same strength of interaction between these two cities and these two others because of the different opportunities involved. And so this is the idea, the intuition behind the radiation law. It's that to predict the strength of the interaction, you need to take into account what is also available at the same distance. So the typical example is when you have individuals looking for jobs in cities. Each city has a number of job opportunities. Each job has a value of interest considered random. What is the probability for a job seeker to choose a job in city C located at distance D? It depends on how many jobs are offered in city at a distance equal or lower than D. And the strength of this model is that it's parameter free. So here are the details of the model. Basically, it's defined by this equation. So the probability of observing an edge between I and j, the strength of the connection between I and j depends on their degree and on S, which is defined here. And this S here is defined as the sum of all the degrees of all the nodes which are located at a distance which is less than the distance between I and j. So let's see on a drawing how to interpret this. You want to know what is the strength of the interaction from between I and J. So for a job seeker in I to find a job in J. Well, it depends on all the other opportunities you have in this circle. So at a distance which is the same or shorter. Okay, and so this comes from the formulation in physics of radiation and absorption. Okay, so but the basic idea is simply that the more opportunities you have at a shorter distance, the less likely you are to move to find a job in such a city. So here is an example of a study. So in the article that introduced this solution, in which they show that if you compare with, for instance, a radiation model which has been fit on the data and then on the gravity one, and they consider that the radiation model is actually more similar to the real data than the gravity one. So the gravity one seems here to overfit short distances, for instance. And if you go to the details, again, you see that the real data is more similar to what is predicted by the radiation model than the gravity model. So maybe you can, if you check the paper, they don't fit really a deterrence function in a way as accurate as what I've introduced here. But so you could discuss the validity of the results. But anyway, since they introduced in this paper the radiation model, they show that the radiation model is interesting, obviously. So to sum up, let's see what are the advantages and the drawbacks of the two methods. So the first advantage of the radiation model is that it has no parameters. You don't have to fit a deterrence function. You just consider that, so you just have to know the position of node and you have your model. Okay, nothing to fit. And two nodes of the same degrees and similar distance can have different edge probability based on their location. So with the examples I've shown before, with the two cities in Vladivostok and the other one and the other which are in the heart of Europe, you see that this makes sense. But the gravity model still has an advantage, which is this customizable deterrence function. And this is sometimes this can be really useful because the problem is that the real world is very complex. And if you take the situation that I've shown, for instance, with the Velov, in which you have a deterrence function which is actually not monotonous, so you have the probability of short distances is smaller than a little bit longer distances, then you cannot model this with a radiation model. Okay, in the radiation model, if you're shorter, if you want a shorter distance, it's always better. In reality, it's not necessarily the case. So if you, for instance, if you think about airplane trips, you don't take an airplane to do 200 kilometers. Okay, it becomes interesting to take an airplane only if you want to do 1,000 kilometers. Even for your car, you're not using your car if you want to buy some butter at the shop, which is just 100 meters away. Okay. You obviously use a car only if you want to go to somewhere which is far enough for it to be efficient to take a car. So in these situations, clearly, you have to be careful and to use an appropriate deterrence function that you cannot do with the radiation model, which has no parameters.